Hi, I'm Ms. Hearn. Let's get started. In this video, we're going to get really good at using the fundamental theorem of calculus, the part where it says that the derivative of the integral is the integrand. So let's really look at what the theorem says, but really this video is about applying it and getting quick with it. So the theorem says if f of x, capital F of x, is equal to the integral from some number a to x of f of t dt. So this is defining a function of x as the integral from a to x of some function. Then if you differentiate capital F, take its derivative, then you're going to just get little f of x from the integrand of the original integral. Or in short, you can say it, you may have seen it written this way, that the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. So we're going to apply this. So the first function that I have is the integral, capital F of x equals the integral from 0 to x of t squared plus 1 dt. So you see this fits exactly the pattern. You can see that in this case a is equal to 0, but in fact that doesn't matter. The derivative of capital F is going to be equal to this function from the integrand, just with an x instead of a t. In this particular case, I could actually prove it to you, but that's not what this video is about. This video is about getting really good at applying it. So now let's look at the next example. Capital N of x equals the integral from 2 to x of cosine of t dt. Again, we've been asked to differentiate that function n. So what is n prime of x equal to? The function from the integrand, which in this case is cosine of t, but we have plugged the x into it, so it's cosine of x. Now let's look at the third one, capital G of x. This is the integral from 3 to x of square root of t dt. Again, it doesn't matter that a in this case is actually equal to 3, just as long as we have some number to x of the square root of t dt. So our derivative of that function, the derivative of that whole integral, is going to be just the function in the integrand, but with an x in it. So we have the square root of x. Let's look at this next one, capital H of x. Capital H of x equals the integral from 0 to x of dt over t. This throws my students off sometimes because we have to identify the function in the integrand, and it's written in a way that confuses folks. So remember, this is the same as the integral from 0 to x of 1 over t dt. So what is the function that's actually in the integrand? 1 over t. So h prime of x is just 1 over x. Now let's look at k of x, the integral from 5 to x of dt over the square root of 1 minus t squared. This is very similar to the previous problem in the sense that the dt is in the numerator. So what will be our k prime of x? What is the function that's in the integrand? Well, think of this as the integral from 5 to x of 1 over the square root of 1 minus t squared dt. So we just need 1 over the square root of 1 minus t squared, but with an x instead of a t. Okay, so those problems are the type where you have an x as the upper bound, and it exactly fits the formula that we have in the Fundamental Theorem of Calculus Part 1. However, we are not always so lucky. Here I have a list of integrals that are very similar to the original integrals, but the upper limit of integration is not just in x. So let's look at y equals the integral from 0 to 5x of t squared plus 1 dt. So this is exactly the same as capital F of x over here. The only difference between these two functions is that one was an integral from 0 to x and the other was an integral from 0 to 5x. In other words, we have replaced the x in the function capital F of x with 5x. In fact, instead of calling this function y, we could refer to it as capital F of 5x, because all we've done is to replace the x with 5x. Now the reason why I'm mentioning that is because our job is to find the derivative, right? And how do you find the derivative with respect to x of a composition of functions? You use the chain rule. And the chain rule tells you to take the derivative of the outer part with the inner still the same, and then multiply times the derivative of the inner part, in this case the 5x. Well, what was f prime? Capital F prime of x, when we took the derivative, was just that inner function written with an x. It was x squared plus 1. So this first part of the derivative is going to be 5x squared plus 1. And we're going to multiply that times the derivative of 5x, which is just 5. So we're going to have 25x squared plus 1 times 5. Which is going to turn out to be what? 125x squared plus 5. But the part that I really want you to focus in on is that all we've done is plug the 5x into what would have been the derivative of the original function with an upper bound of x. We've just replaced it with 5x. And then, because of the chain rule, multiplied by the derivative of 5x. Okay, now let's look at the next one. We have y equals the integral from 2 to x squared cosine of t dt. This is exactly like the function n of x that we looked at before. Equals the integral from 2 to x cosine of t dt. The only difference is the upper bound is the function x squared instead of x. So whenever you notice that, all you do is, instead of saying that dy dx equals cosine of x, as we would have if there were just an x up there, you are going to say cosine of whatever is up here, which is x squared times the derivative of x squared. In this case, that would be cosine of x squared times 2x. All right, let's look at the next one. We have y equals the integral from 3 to e to the 2x. This is just the same as the function capital G of x we had before. It's just that we have e to the 2x instead of just x. So this is going to be dy dx equals, instead of square root of just x, we're going to have the square root of e to the 2x times the derivative of e to the 2x. So that's going to be e to the x times 2e to the 2x. And that's going to be, let's see, 2, adding the exponents, e to the 3x. Let's look at the next one. We have y equals 0 to sine of x dt over t. This is just like h of x equals dt over t from 0 to x, but instead of an x, we have a sine of x. So keeping in mind now that this means the integral from 0 to sine of x, 1 over t times dt, then our derivative dy dx is going to be equal to, instead of 1 over x, it's going to be 1 over sine x times the derivative of the sine of x. So that's going to be 1 over sine x times cosine of x, or cosine x over sine x, which is cotangent of x. And finally, we have the integral from 5 to natural log of x dt over square root of 1 minus t squared, which is just like the k of x that we did. So its derivative, dy dx, would be 1 over the square root of 1 minus x squared, but we're replacing x with natural log, so it's going to be natural log of x quantity squared times the derivative of the natural log of x, which is 1 over x. So we have dy dx equals 1 over square root 1 minus natural log of x squared times 1 over x. And I'd probably just say x times the square root of 1 minus natural log of x squared in the denominator. I hope you found this video helpful. If you did, please give it a thumbs up. That helps other students to find the video. You can also follow other links to some of my other calculus videos or subscribe to my channel.